All right, guys, welcome to our lesson for today. Actually, because we didn't get to do a lesson yesterday, I decided to go ahead and prepare two lessons for today. We're actually going to be taking care of, and these are pretty heavy lessons, by the way. They're pretty detailed. And I think you're going to find that you're going to learn a lot in these lessons because we're getting into the areas of OSPF that maybe you don't, you're going to see situations you don't normally run into that often, maybe because the design doesn't really call for this type of implementation. And so we're going to see quite a few new things today that would be very specific to something that they would perhaps ask on the CCIE exam, but maybe wouldn't require you to do, in the real world. So both of these lessons, lesson number one, and I'm going to record these as separate lessons today because they are kind of in-depth. We're going to do controlling NSSA redistribution and take a look at, all of the different scenarios of how we redistribute routes into an NSSA, the not so stubby area. Who's allowed to do the redistribution? Is the redistributed route going to have a local scope? Can it be translated to a type 5 by setting the P bit? And how do we identify what that P bit is? And what is the effect of having the P bit turned on or the P bit turned off? It's something you definitely could see potentially on the lab exam. Definitely, potentially, that would be probably counterintuitive. But anyway, these are scenarios that are basically design case scenarios, which is what the CCIE loves to test on. Maybe not necessarily something you would normally see in a production environment, but something you would see specifically in the lab. Okay, and then we're going to wrap up today by doing a next lesson, which is default routing with OSPF NSSAs as well. I don't think it's going to take 3.5 hours, but they're going to be let's just say meaty discussions, if you will. All right. So we're going to be using this topology. We'll be making some modifications to this topology as part of the process. Somebody just sent me a Slack message. Hold on one second. We will be making some modifications to this topology to kind of facilitate our discussion because, again, like I said, what we're going to be looking at is setting up Area 2 as an NSSA. So in this particular topology, this area here is going to be our NSSA. And then we're going to have some information running into Area 0 that we would also have in Area 2 as well. So we're going to be taking a look at several different scenarios. How does Router 4 prefer the route in and out of to the external network? Is it going to prefer something from Router 1 or Router 5? Is it going to prefer an E1 over an E2, an N1 over an N2, and so on? And that's what we're going to be taking a look at. So let's start by, in this lesson, controlling the NSSA redistribution process. All right, so it is kind of a continuation of the discussion that we had in our last lesson, where we're going to be manipulating this not so stubby area to do redistribution of external routes into the domain. In this case, I'm going to add a external router. Let's go ahead and do that right now, actually. And rather than just redistributing a loopback, I'd like to have a physical router that's going to allow us the ability to control how the routes go into the domain. So let me go into Router 3 real quick, and let's remove the, it's already started. Let's remove the loopback 192.168.3.0, or excuse me, loopback 100, which we were redistributing from EIGRP into OSPF. All right, so let's do a show IP protocols. Yep, we're running EIGRP 100. We'll go ahead and leave that in there. Show run pipe section router. And let's get rid of the redistribution for now. Oops. Helps if I type it correctly. We'll get rid of the redistribute EIGRP 100 subnets. You know what? I'm going to leave that in there for now. I thought I was doing a redistribute static, but we're doing a redistribute EIGRP 100. So let's just get rid of show IP interface brief. Let's get rid of loopback 100. And let's go ahead and create our stub EIGRP router. So we'll just call this guy EIGRP. Yeah, we'll just call this guy EIGRP. All right, and let's create a path. Let's do Ethernet 1.1 to oh, I see. We're using. Let me do this. Forgot we weren't using our IOSV in this topology. So let's go ahead and grab that router instead. I'm sure the IOSV routers can talk to the iOS routers, but let's just keep it consistent here. All right. We'll connect Ethernet 1.1 to Ethernet 1.1. And as we talked about the last time, when we're doing redistribution from a domain that's outside of OSPF into OSPF, those routes will either come in as a type 5 route or they're going to come in as a type 7, depending on what type of area they're coming in from. So let's do Ethernet 1.1. I'm going to save this topology for you guys later, so I want to have it all kind of documented here so you know what you're looking at as you're reviewing the video. And let's make this subnet 172.16.100.0/24. I think that's cool. Yeah, that should be okay. All right. So let me start the router. If I go back into router 3, config T interface Ethernet 1.1, IP address 172.16.100.3. No shut. Network 172.16.100.0. All right. And let's go into router EIGRP. Ethernet 1.1. And let's join that guy to EIGRP. So we should get an adjacency. All right. Now let's also create a loopback on this router. And we'll just call it 100.100.100.100, 255.255.255.255. And let's go router EIGRP 100. 100.100.100, 0.0.0.0. All right, so what I should be able to see now on router 4 is I should be able to see those routes coming into area 0 as type 5s, but I also should also see those routes on router 5 and router 1 as type 7s, okay? Now, the first thing that I want to see are these external routes that are coming from router 3, because remember router 3, let me put that on the diagram here. The router 3 is my ASBR, because we're doing our redistribution on this router. So router 3 is my ASBR. The question is are these external routes going to be area local scope, or can they be translated into a type 5? The way that we can identify that is to look at the OSPF database on router 1 and router 5. So let's go into router 5 and take a look at the database. And we should see, let's do a show IP route first of all. Pipe include E1, E2, N1, N2, and see if we see any of those routes in the database. And we can see, in fact, that we have two routes coming in, 172.16.100, which is the network prefix between the EIGRP router and router 3, and the loopback that we created on the EIGRP router is coming in as an ON2. So that indicates to me that those are coming in as a type 7. We also see a 198.51.100 that's coming in from router 4, I believe, which is acting as kind of our internet router going out to this internet routing domain out here. So this route is being redistributed in as well from router 4. But we're going to focus primarily on the EIGRP domain in this particular topology. So when I say that a route that's being redistributed by an ASBR into a special area has a local scope, or it can be translated into a type 5, we want to take a look at the NSSA external routes on the ABR. So if we go into router 5 and I do a show IP OSPF database, NSSA external, we can see here that the routes are coming in as a type 7. The routing bit is set, which means that these routes are valid. These routes can be used. They're reachable. The forwarding address is identified as 192.168.3.1. Now keep in mind, that is not a node identifier. That is a link identifier. So we need to be able to recurse to 192.168.3.1 to be able to reach these external routes. This is the node identifier, the advertising router, 3.3.3.3, but the forwarding address is the actual link identifier. If I do a show IP interface brief, we can see that the forwarding address is not router 3. The forwarding address is a different router. If we look at our topology here, most likely that forwarding address, well, it's going to be R5's interface, I believe. So let's take a look at R5, show IP interface brief. Actually, forwarding address is 3.1. Yeah, it's the loopback. Yeah, the forwarding address, and I was going to show you guys this a little bit later on, but the forwarding address is typically always going to be the highest loopback on the router that's originating the external routes. So if I was to come into router 3, for example, and do a config T interface loopback 1, give it an IP address of 192.168.33.1, and then IP OSPF 1 area 2, and add that to the domain. If I come to router 5 now, I should see that after I reconverge here, that forwarding address should change to 33. Let me make sure I put in the right area. OSPF 1. OSPF 1 area 2. Show IP. OSPF database self-originate. Router self-originate. I just want to make sure that that 33 is being sent in. Yeah, it is being sent in. Okay. So I should see, in this case, I wonder if it's something that would, So usually it's supposed to be the highest loopback would then be indicated as the forwarding address for that destination. We'll take a look at that again a little bit later on in this lesson. It's not really what I'm trying to demonstrate here. But what I do want to mention, though, is that the forwarding address is not a node ID, right? If I do a show IP protocols on router 3, the node ID is 3.3.3.3. Loopback 1 is in area 2. So I'm very curious why show run interface loopback 0. Let me just do one more thing. I wonder if network type has an effect on it. I might have to verify that, but my understanding was that the highest IP address on the loopback interfaces ends up becoming the forwarding address. Let me try to clear the process on router 3, because if I clear the process on router 3, it might clear IP OSPF process. It might advertise a different forwarding address for those external routes that it's originating. Let me see here. Yep, still sending in 3.1, so not sure. I'll have to take a look at that. But in any event, let's talk about what I wanted to show you, which is are these external routes considered to be local scope, or can they be translated into, can they be translated into a type 5 and sent out of the area to the rest of the domain? And what you're looking for here is the options, type 7 to type 5 translation. Type 7 to type 5 translation means that the route is allowed to be translated at the ABR and sent into the domain as a type 5. So our type 7 routes are going to become type 5 as they go through the domain. When a router, especially an ASBR, does generation, there is a field that gets set. It's called the p-bit field. And that's what represents whether or not this translation is going to be allowed or not. There are some additional arguments to redistribution. If I come into router 3 and I do a show IP OSPF or show run section router, we're just doing basic redistribution from our EIGRP domain into our OSPF domain. We're just redistributing EIGRP subnets. Actually, I'm going to need to probably eventually redistribute OSPF back into EIGRP as well, because we're no longer using connected networks. So to get our full reachability, we're going to have to do mutual redistribution, but we'll wait to do that in a little bit. All right. If we're looking specifically at the NSSA area, we want to make sure that we understand what those arguments are for doing the redistribution, and specifically within the NSSA. So if I come into this router here and I do a config T, don't know why it's not taking my letters, config T, router OSPF 1, we know that we can establish this as an NSSA by simply typing in area 2 NSSA. Now, by definition, if you guys recall from our last discussion, an NSSA is essentially a stub area that allows the addition of an ASBR. So what types of LSAs are normally going to be allowed into this area? Type 3s, and then internally type 1s and 2s, and type 7s, which represent those external routes that we're redistributing into the area, based on the fact that this is an NSSA. But if I use my question mark here, I can see that I have quite a few options with regard to how I set up the NSSA. Am I going to generate a default route into the NSSA area? We'll talk about that a little bit later. Am I going to do no redistribution? Am I going to do a no summary? No summary would basically is the command that you would execute on the perimeter router, the ABR in the area, to suppress those type 3 LSAs from coming into the area as well. So we do have lots of options. One of the things that I did prior to the class is I pulled up what some of the descriptions are. And if you were to look at the command reference, this is the command reference for 15x. For the area NSSA command, you can see that we have the options. No redistribution is used when the router is an NSSA area border router and you want the redistribute command to import routes only into the normal areas but not into the NSSA. Okay, so what that means is in our particular example, if I was to go into this topology and take router 5 and make router 5 an ASBR, have maybe a link that comes over to the EIGRP router, and do redistribution on router 5. Is router 5 going to send in the type 7s into the area, into the NSSA, and is router 5 going to send, let me go ahead and draw a little diagram here, because it'll be a little bit confusing otherwise. So what I'm saying is, what if I take a connection here? Now I make this guy an ASBR, right? What happened? Come on, seriously? Let me do it a different way because the annotation tool on WebEx stinks. Let me just use my snipping tool. So let's say again, I go ahead and connect that router to EIGRP, and I make this guy an ASBR. Right? Now that means that I'm doing redistribution into router 5 from an external domain. But because router 5 is part of this NSSA, normally it would send in type 7s here, and it would send in my type 5s there. Now you can see where that could be somewhat problematic. Do I want the type 5s to go into area 0 and the type 7s to go into the ASB or the NSSA? Well, the no redistribute command allows us to essentially suppress that from happening. All right. So let's take a look at the demonstration. I wanted to demonstrate a lot of these concepts, which is why the lesson's a little bit more complicated, because we're going to get into some pretty unique stuff. So like I said, I wanted to kind of demonstrate each of these concepts to you guys because I want to make sure that you understand really the details about what each of these options are. And that's where a lot of people get hung up on the CCIE, is they tend to lack focus on the details. So it's highly likely on the exam that they're going to ask you to say, they'll say, let's go ahead and send in a default route from an ASBR in an NSSA, and let's send in a default route from an ABR that's attached to the backbone. And let's have some routers choose one route, the route from the NSSA, and let's have other routers choose the route from the ABR to leave the area. It's a typical traffic engineering scenario that you have to be concerned with. So it's really important that you guys understand not only the basic concepts of setting up an NSSA, but you also understand the need or the arguments that could be used for the process itself. Okay, so what we're going to do is we're going to go ahead and set up.
Stop.
Yes.
Don't mean to interrupt, I do, but so I just wanted to make sure, and this is a stupid question, but it's been bothering me. An ASBR and an ABR are similar, but an ASBR redistributes and an ABR doesn't. Is that correct?
Correct. Yeah, an ABR is just any router that is attached to the backbone area, but is not and is also attached to a non-backbone area. An ABR can be an ASBR, and an ASBR can be an ABR. So as it is right now, router 5 is simply acting as an ABR, right? If I go into router 5 and I do a show IP OSPF database self-originate, show IP OSPF database self-originate, you can see that I am not generating any of my own type or external routes. I'm of course generating type 5s because the type 7s are becoming type 5s when they leave the area. Remember, these are the routes, these are the EIGRP routes that are coming from the EIGRP router. So I am generating type 5s, but I'm not doing redistribution. Go ahead.
Right. So when you have a type 7, that means that you're not supposed to, or that doesn't get redistributed anywhere else. It just goes into an area and says, hey, these are the routes that are going out. But you don't want them to pass that on to somebody else or another area unless there's another ASPR that's doing it. And then it'll translate it to a type 5 as it redistributes.
No. Type 7s always become type 5s when they leave the area. And that's the responsibility of the area border router that's attached to the NSSA and the backbone. So
why have a type 7 then if it's always going to become a type 5?
Well, there's a couple of reasons. Number one, we can control the scope of a type 7. We can identify whether or not it's going to have a local scope within the area, and it doesn't leave the area by setting the P-bit of those type 7 routes. And number two, type 5s are not allowed into a special area type. That is the golden rule, right? If stub, totally stubby, not so stubby, totally not so stubby, type 5s are not allowed in. So they have to come in as type 7s.
And that says, yeah, you can go ahead and put it in here, and that's all it is, unless you go ahead and change the bit type, and then you change it back to a 5 and go someplace else.
Yeah, well, the P-bit doesn't indicate that it should be changed to a type 5. That happens automatically. The P-bit indicates whether or not it's allowed to be changed, right? So if I do a show IP OSPF database NSSA external, what we're looking for specifically is whether that type 7 to type 5 translation is going to be allowed on those routes. That's what the P-bit identifies. If I was to capture the LSAs, these type 7 LSAs, in the LSA there's a P-bit value set, which by default is turned on, that allows me to identify whether or not those routes are allowed in. So here's what we're going to do. I want to demonstrate, hopefully that answered your question, Tim. So we're not...
But you'll be explaining about how to get rid of the P-bit.
Yes. So if I do a show run section router on router 5, which remember is my ABR, I'm not doing any redistribution. Okay? So just to reiterate, the conversion of a type 7 to a type 5 is not a redistribution process. It's a normal OSPF process as long as the P-bit is set on those type 7 routes that are being injected by the ASPR and the NSSA. Okay? So what we're going to do is we're going to create a loopback interface, and on the ABR, we'll get rid of this guy a little bit later on. So interface loopback 55, IP address 55, 55, 55, 55. All right. And what we want to do is we want to just kind of redistribute this this interface into OSPF, not all the connected interfaces, but just this interface. So let's do a route map, and we'll just call it connected 55. And let's just do interface loopback or match interface loopback 55. And let's go into router OSPF 1. And we'll do a redistribute connected subnets, and based on route map connected 55. All right, so if I do a show IP OSPF database self-originate, I should see that 55, 55, 55, 55 being generated both as a type 5 and as a type 7. Okay? We can see it's generated as a type 7 into area 2, and it's generated as a type 5 into the backbone area, along with the other routes that we got from the ASBR in the NSSA, that's with a router that's connected to the EIGRP domain. All right. So when it goes into the NSSA, no one else is going to be able to translate it back. All right, so we could have an issue where we have multiple ABRs, and that's going to create a loop in the topology, especially if I've got routes coming. We don't have it right now, but if I had routes coming in from that external EIGRP domain to this ABR, and I was sending those into the NSSA along with router 3, who's already sending them into the NSSA, that would be a bit of an issue. So let me do a show IP OSPF database, NSSA external 55, 55, 55, 55. All right. Now we can see here that no type 7 to type 5 translations are allowed. Now why is that? We didn't change the behavior of the route. We simply just did redistribution on an ABR, making it also an ASBR into area 2. All right, so the P bit was automatically disabled in this particular case as a loop avoidance mechanism in OSPF. And here's the reason why. If I go back to my topology, we're okay the way it is right now because we've created this, if you will, this loopback on router 5, and we're redistributing that. So that's coming in here as a type 5. It's coming in here as a type 7, but that P bit is off in this case. Well, guess what? I don't want that type 7 to come over here, go over to router 1, and then be sent in as a type 5 into area 0 as well, because we're already originating that route into area 0 as a type 5. If I go to router 1, we can see if router 1 sees that route. All right, let's go into router 1 and see if we should see the type 7. Show IP route pipe include E1, E2, N1, and N2. And the 55, 55, 55, 55 is coming in as an OE2 route from 14.3, which is in area 0. So, but if I do a show IP OSPF database, I can see from my type 7 list that we are getting the 55, 55, 55, 55 route as a type 7 in the area. So if I do a show IP OSPF database NSSA external 55, 55, 55, 55, again, no type 7 to type 5 translation is allowed for this particular route. If I do a show IP OSPF database self-originate, I should not see the 55, 55, 55, 55 anywhere as a self-originated route because I'm not doing the conversion from a type 7 to a type 5. Now, that happened automatically. We didn't have to do that in this particular case. In other cases, we might have to control that particular process. All right? We'll talk about why that is a little bit later on. Okay? So, in the actual packet payload of the LSA, that P bit is what's being set to indicate this particular behavior. All right? Now, what if I did not want to redistribute that type 7 into the domain at all, right? In other words, I don't want to send, I want to send the type 5 into, let me go back to my diagram here. I want to send the type 5 into the backbone, okay? But I don't necessarily want to send the type 7 in at all. Because we might be using a default route to get out of the NSSA. We may choose to use a different path to get out of the NSSA, so I don't necessarily want to send in the type 7 at all. And this is where the arguments come into play. They might say on the lab, go ahead and use, let's go ahead and redistribute a route from router 5, the ABR, but don't send it into the NSSA, only use the default route in the NSSA to reach that external network. And you have to be able to understand how you are going to accomplish this task by using the different arguments within OSPF. So if I go to router 5, Now this would affect all of the, and I do a show run pipe section router. I've already established that area 2 is an NSSA. So if I go into router OSPF 1, and I can't type this morning, router OSPF 1, area 2 NSSA, and I use the no redistribution option. All right, now if we look at the description of that again on the command reference here, used when the router is an NSSA area border router and you want the redistribute command to import routes only into the normal areas but not into the NSSA. Meaning that I'm not going to send this type 7 in for the 55, 55, 55, 55 subnet. I'm just going to send it into the backbone. All right, so let's go ahead and do that. And let's do a show IP OSPF database. Self-originate. And you should see now we're no longer sending a type 7 for the 55, 55, 55, 55 network. We're only sending the type 5 into area 0. All right? So that's one of the options where we say, okay, no type 7s are going to be allowed. But this would only be something that would be affected on the ABR that's attached to the NSSA and a normal area that you're actually converting into, or at least configuring as an ASBR as well. All right? All right, but what if I said, you know, my task was, okay, in this case, let's not send in the type 5. So we're going to do no type 5, and we're going to send in the type 7. Again, these are all specific design case scenarios. These are situations where you're required to, you know, meet a specific objective or meet a specific goal, most likely because the CCIE is requiring this, and this is where you have to understand the arguments that are available with the NSSA configuration. So let's do a show run section router. So just to be clear, the no redistribution command doesn't mean we're not allowed to redistribute routes. It just means we're not going to take those redistributed routes and inject them as a type 7 into the NSSA. So let's go into router OSPF 1 and let's do area 2 NSSA, and let's do NSSA only in this case. It should be NSSA only. We don't have that option here. I wonder why it's not providing that option. Let me go back to my notes here. This syntax is not giving me that option. Limits the default advertisement to this NSSA area by setting the P bit in the type 7 to 0. Ah, okay, yeah. Well, that should still be an option. Let's go to router 3. This might be something we need to do on router 3. So we're sending, yeah, it's not an option here. Maybe NSSA only here. No. Well, that stinks. This code does not support that. But let me describe what that would do. If I was to do the NSSA only here, I'm not sure why this particular code is not allowing us to do that. But if I had this option enabled, I would not send the type 5 into area 0, but I would send the type 7s into the NSSA area 2. All right? So let's now create a network between the router that's in area 0 to the EIGRP router. Add that to the EIGRP process so that we have two ways of reaching this external domain. So now we're going to add a link here where the ABR is going to become an ASBR for the EIGRP routing process. We'll do mutual redistribution on both sides. So router 3 into EIGRP and from EIGRP into OSPF, and router 5 the same thing. Let me go to my topology here, And let's, just to make it look kind of cleaner here, let's add a switch, a fake switch, if you will. Where is my fake switch? There it is. All right. And we're just going to connect, we'll just call this some LAN. And we're going to create a subnet from router 5. Let's make this Ethernet 1, 2. And same thing on this side, Ethernet 1, 2. Again, this would be a very, very specific design scenario where you might have an extranet connected, or maybe you have some sort of redundant connection to an external domain from multiple routers. All right, we're going to make this guy, this will be Ethernet 1, 2. And this will be Ethernet 1, 2 also. And we'll just make this subnet 101. 172.16.101.0/24. So on router 5, let's go to router 5. Interface Ethernet 1, 2, IP address 172.16.101.5. No shut. We're going to run EIGRP 100, and we're going to put that network into EIGRP. We'll do our redistribution in a little bit. Let's go to our EIGRP router. Should get an adjacency. All right. We should have two neighbors. Did I forget to turn on the interface? I did. Now we should get an adjacency. All right. So now our topology is slightly different. In this particular case, we have this router here that has reachability to this EIGRP domain, and then this router here that has reachability to the domain. So this is where it gets really complicated, because when I send the routes in, are they going to come in as an OE1? Are they going to come in as an OE2? N1, N2? What's the order of preference for selecting the path? And I think you're going to be really surprised, based on documentation, what that selection process is. So let's go ahead and redistribute into OSPF. And let's redistribute from EIGRP into OSPF, and from OSPF into EIGRP. So let's go to router 5, show run pipe section router, just to see what we have presently. And let's do a config T router OSPF 1. Let's do a no redistribute connected. And we're going to do a redistribute EIGRP 100 subnets. So we're going to send the routes in to OSPF, all of the routes in to OSPF that are part of EIGRP. And we'll just do the default right now. And let's go into router EIGRP. And we're going to do a redistribute OSPF 1 metric. We'll just make something up here. 10,000, 10, 255, 1, 1500. And let's do the same thing on router number 3. Do show run pipe section router. All right. And let's do, we're already doing the redistribute subnet, so let's go into router EIGRP 100 and redistribute OSPF 1 metric 10,000, 10, 255, 1, 1500. All right. So if I do a show IP route, I should see DEX routes and OSPF routes. The OSPF routes are going to be preferred over the DEX routes because they have a lower administrative distance. But if I do a show IP EIGRP topology, I should see that I have quite a few routes in my topology database. So I'm getting my routes from EIGRP into OSPF, and I'm getting my OSPF routes into EIGRP, and I should have full reachability. If I come into router 4, we're not going to look specifically at how router 4 is reaching a destination right now. Let's just see if we can reach the destination. So ping 55, 55, 55, 55, which I should be able to ping. You know what? I didn't add that loop back. I did a redistribute connected on that. So if I do a show IP protocols, 55, 55, 55, 55 is not running. Yeah, is not part of the OSPF process. So let's, our EIGRP process. So let's go ahead and add that as well. I don't know if we're going to use that route a little bit later, but let me see. Yeah. All right, so I see if I do a show IP route, pipe include E1, E2, oops, N1, and N2. I can see that everything is coming in as an OE2. That makes sense on router 4 because router 4 is in area 0, and all the type 7s are going to get converted to type 5s anyway. All right, but the question is, how am I going to choose to route? And you would be surprised whether or not I would choose to route via the N route or the E route. We may have to make a couple more modifications to our topology diagram so that we have a couple of ways for router 4 to reach those external networks. In fact, I'm probably going to have to add another link up to the other ABR. But let's continue on right now, and if we need to add some more, we will. Okay. So this is a very specific design case, right? Obviously, this is probably not something you're going to see in a real production environment. But again, you need to be prepared for just about anything on the exam, even if it falls out of standard design scenarios, which is why it's really important to understand this. So we've got multiple ASBRs that are now originating this external network. One is going to be a type 7, one is going to be a type 5. So I have to make a decision. Am I going to use an E1 route over an N1 route, or an E2 route over an N2 route? All right. Now, let me think about this a second. So let's look at our topology real quick. And I may have to... Yeah, that should work. That should work because if you look at the topology here, router 4 has a choice. Let me grab another snippet of this topology now that we've changed it. Router 4 is going to have a decision. Actually, router 1 would most likely have a decision. So router 4 is most likely going to choose, well, it's going to be an OE2 route regardless because we don't have a type 7 coming into the domain. But if you look at router 1's perspective, router 1 could choose to go this way to get to this external network, or it could choose to go this way to get to the external network. So router 1 is trying to make a decision, am I going to use the type 7 or am I going to use the type 5, right, to get to that external domain? What do you guys think? That's the difference between an N2 route and an E2 route in this particular case. Now, traditionally, we've always stated that an OSPF route, O routes are preferred over OIA routes, and then E1 is going to be preferred over E2, or E1 is preferred over E2, and N1 is preferred over N2. But that's actually not technically the case, and we'll take a look at that. I'm just trying to think in my head how I want to demonstrate this, but hopefully we'll be able to see this on router 1. All right.
One is the when you're looking at the metric for that, I mean, the total cost, you're looking at the metric of the total route. Whereas with the N routes, you take it from the actual redistribution point, so you can change it right there on the spot. Like say if it's a total of 50, and that's more than what you want it to go over that, you could change that to say 20 or 10.
Well, so
and then that'll take precedence.
So I understand what you're asking, and let me explain the difference here. First of all, that's a common misconception that that the metric of the external route is what's used to decide how to get to that destination. That was actually one thing that I wanted to demonstrate in the next lesson if we get to it today, based on how much time we're taking on this one. But in the next lesson, I wanted to demonstrate this concept of that we don't actually use the external metric, the metric that's tied to the route, to decide if we're going to choose an E1 route over an E2 route or an N1 route over an N2 route. It's the forward metric that we need to look at. So, but I'm going to get into that. But before I do that, let's talk about the difference between E1 and E2 and N1 and N2, right? When you inject a route using as an external type 2, the seed metric does not increment as you move through the domain. The seed metric stays the same. So if I inject a default route, redistribute a route into OSPF and the seed metric is 1 or the seed metric is 20 or whatever, it's going to stay that throughout the entire topology, regardless of whether it's an E1 or E2 or an N2. Both of those have the same behavior. So the decision that I have to make is not based on the metric that's tied to the route. The decision that I have to make is whether or not it's an intra-area external or an inter-area external, or what is the cost for me to get to the node that is advertising that external route, if that makes sense. It probably doesn't, but I'm going to demonstrate that a little bit later in this lesson here. My point is, and hopefully we'll get into it in more detail in this lesson, if not the next lesson, but my point is that the common conception that somehow external E routes are going to be preferred over N routes is actually not true. It just depends on what the forwarding metric is for those external routes. The only time that an E route would be preferred over an N route is if the forwarding metric is the same for that particular destination. So let's see what I know I didn't completely answer your question, Tim, but I'll keep it in my mind here, and I'll continue to try and describe. This is the kind of thing where you really kind of have to see it to understand it. So let's go to router 1. And let's take a look at how router 1 is forwarding to that 172.16.101 network. So if I do a show IP route 172.16.101.0, we can see that the route is coming in as an external type 2. But if I do a show, let me look at my topology here. If I do a show IP OSPF database, NSSA external, I can see that prefix. Let me just do a show IP OSPF database. Type 7. Begin type 7. Sorry about that. So I can see that the 172.16.101 subnet is coming in as a type 7 on router 1, and it's coming in as a type 5 on router 1. Okay? Now, if you look at the topology, it doesn't really, the cost is the same, right? The forward metric to get from router 1 over to router 3, because of this is an EIGRP link. The cost of this link is not being included in the overall path cost. We're injecting the route here with a cost of 20, and we're learning the route from router 5 with a cost of 20. So if I come back to router 1 and I do a show IP route 172.16.101.0, you can see that the metric here is 20, okay? But the forward metric is 10. Now what does that mean? That means that the overall path metric is 30 for that external prefix. The forward metric is the cost essentially for me to get to the router that's advertising that particular route, which is just our LAN segment, which has a cost of 10. Now, if you consider what the forward metric is for the N2 route, here the forward metric is the same because this is also an Ethernet connection. Does that make sense? So what if I was to change that behavior? What if I was to make the forward metric for this link higher? This is still an E2 route. This is an N2 route. Is the E2 route going to be preferred over the N2 route? And it's always been stated that E2s are preferred over N2s. But it has to do with the actual forward metric, not the seed metric, but the forward metric. Certainly you could affect routing based on changing that seed metric because it is a cumulative metric value. So if I was to say inject this external network with a seed metric of 1 as opposed to 20, then the forward metric, well, the forward metric is still considered, but the overall path metric would still be lower. Let's do that first and see if that changes any of the behavior. So I'm going to redistribute the EIGRP routes from router 3 into the domain, but I'm going to change the seed metric to a 10 rather than a 20 to see if that affects my path selection process. So let's go to router 3. Show run pipe section router. Oh, jeez. And let's go into router OSPF 1, and we're going to do a redistribute EIGRP subnets, but we're going to set the metric to 10. All right. So now if I go to router 1, you can see that I actually did choose the NSSA route over the E route. So type 7 in this case is being selected over the type 5 because the forward metric added with this seed metric is less than the overall path metric for the other path. Because that's, well, actually the forward metric is 11, sorry. Why is it 11? Let me look at the topology here. So the forward metric is 11. We're putting in 10. Okay, that makes sense. Well, does that make sense? Because the path cost, this Ethernet link should have a cost of 10. Why is it coming in as 11? And the forward metric is higher in that case. Let me check something real quick. So we're going to 13.2, which is Ethernet 1.2. So we're going in this direction to get to this external network now. I'm trying to figure out why it's creating a forward metric of 11 though, because we should be sending it in. Show IP OSPF border routers. To get to router 5, to get to router 1, I have the cost of 10. So that's correct. And to get to router 5, I have a cost of 64. Show IP OSPF. We do a show IP route 172.16.101.0. So that's coming in from OSPF Well, it's coming in from EIGRP into OSPF, administrative distance of 90. That makes sense. Show run section router. I mean, it's doing exactly what I expected it to do, but I'm not seeing the numbers that I should expect to see with regard to the actual seed metric. The seed metric is 10. If I do a show IP, let's go back to router 1. Show IP route pipe include N2. So this is what I would expect to see. The cost is 10. But what I'm curious about is why it's identifying a forwarding metric of 11 as opposed to a forwarding metric of 10. That's the part that's kind of confusing me. So if I do a show IP OSPF database 172.16, oops. Let me do show IP route, sorry. 172.16.101.0. This is the number that I'm trying to figure out why it's 11. The forwarding metric should be 10. I'm not sure why it's 11 in this case.
Hey, Scott, if you're redistributing on router 1, could that just add a 1 to it? Not that it's router 1, but because you're redistributing there and you're trying to get that same metric, or if you're doing a
well, I'm not actually doing any redistribution on router 1. Router 1 is just participating in OSPF. It's learning about the route through the NSSA, and it's learning about the route through area 0 as an E2 route. And that was the point that I was trying to make, is that the overall path metric for the external type 2 route is now higher than the path metric for the NSSA route, the N2 route. So to say that E2 routes are always preferred over N2 routes is not true. That's kind of the point that I was trying to make. So we are taking the NSSA external type 2 route. This is the metric that's being sent in with the route, but I'm really curious why it's reporting a forwarding metric of 11. Let's see what's happening. Let me go back to router 3. And let's just take that out. Router OSPF 1, show run pipe section router. Okay, so now if I go back to router 1, it should change. You know what? I know why it didn't change. Let me do. I have to take out the redistribution command and put it back in. That's a kind of a weird thing with OSPF. Some of the commands, it doesn't replace the command, it just adds arguments or removes arguments. So I have to go back into and do a no redistribute because it didn't take out the metric 10. And then let's do a redistribute EIGRP 100 subnets. Now if I go back to router 1, right, this is what I would expect to see. The forwarding metric is 10 because that's how I'm resolving the tree to get to the router that's originating the route. You see what I'm saying? There must be something with an NSSA route that adds the 1. I'm not sure what it would be. I'd have to go and take a look at that. But what I would expect to see is 10 and 10. With the metric being 10, because that's what we seeded the metric as when we redistributed it, and then the forwarding metric to reach the advertising router would be a 10 as well. So because we've essentially made the paths the same, let's do show IP OSPF database. Database NSSA external. I'll bet you, oh, you know what it is? I know what it is. Because the forwarding address is the loopback, we're adding the cost of the loopback on top of the cost, the overall path cost. And the loopback, because it has a bandwidth, we can test that theory, but because it has a bandwidth of, above 100 meg, it's going to have a cost of 1. That's what's happening in this case. Because again, this type 7 is coming in from router 3, but the forwarding address is identified as the loopback that's on router 3. So if I was to go into router 3, we'll test this theory, interface loopback 0 and do IP OSPF cost 5, for example, and I go back to router 3, router OSPF 1, redistribute EIGRP 100 subnets metric 10. Now, if I go back to router 1, I should see, yeah, exactly. So that's where it's coming from. And this is, again, I didn't know this, but it's actually adding the cost of the forwarding address interface to the overall path metric, even though that address is already on that particular router. Just one of those weird things that you see with OSPF that you would never suspect would happen, right? And these are the kinds of things that they would most likely bring up, in the lab. As just kind of one of those expert level things that you would have to know. And through experimentation, we were able to identify that. So the N2 route is still preferred because the overall path metric is 25, as opposed to the E2 route, which is a path metric of 30. Okay? So in our particular case, we are preferring the N2 route over the E2 route. That's really an important concept to understand because it's not the actual metric of the route. All right. In fact, let's, because the metric is different, how can I prove to you guys that it's, because you might look at this and go, well, yeah, of course it's going to prefer that one over the E route because the E route has a metric of 10. But let's change the behavior. Let's make the seed metric the same, but make the forwarding metric less. So in this case, how would we do that? We would have to come into the topology, and we would still send this in with a 20, and we'll send it in here with a 20, but this is going to come in as an E2. This is going to come in as an N2. But what I want to make sure is that the forwarding metric is higher. So I'm going to change the cost of this link to 15. And we'll just, actually, all we need to do is maybe change that cost of that link to 12. It's going to have to be higher than 11 because we're going to add the cost of the loopback along with this cost. So we're going to have 10 plus 1 plus 20 is going to be overall 31. So let's go into router number 1. And I'll explain what I'm trying to do here when we look at the actual database. So I'm going to go into Ethernet 1.0. I'm going to change the path cost of Ethernet 1.0 to 12 on router 1. Config T interface Ethernet. Which one was it? 1.0. IP OSPF cost 12. All right, now I'm going to go into router 3. We're going to do no, and let's do, oops. And let's do redistribute, and we'll just take off the metric. Also, let's go into our loopback. Do show run interface loopback 0 and interface loopback 0. No IP OSPF cost 5. All right, so here's the scenario. Do show IP. Well, let's do a show IP route 172. Well, that's just going to be the EIGRP route. Show IP OSPF database NSSA external. So we can see that the 172 network is coming in right here, 101, is coming in with that's a metric of 10, but it's coming in as a type 2, which means that this is the metric to reach that destination, but it's coming in as a type 2, and the translation is allowed. But we should see now, let's go back to our diagram. So what's happening in this case now, both routers are sending in the route as a type 2. All right, this is an N and this is an E. They're both using the default seed metric, which is 20. Okay, which means in this particular case that if the forwarding metric is the same, we would choose the E2 route over the N2 route. But by increasing the metric of this guy to 12, that means that this overall path metric is 32. And we already know that the loopback is going to add a cost of 1 because that's the forwarding address for the external route. And the cost of this link is 10. So this should be a 31, which means that that path, the N path, should be preferred over the E path. So let's go to router 1. Show IP route 172.16.101.0. And sure enough, why is it still coming in as a 10? Show run pipe section router. Probably didn't take out the metric type, or the metric, yeah, didn't. This is the kind of stuff that will just kill you on the lab, by the way. Being able to find these problems quickly is really important, right? That's extremely important because they, like I said, they could be really specific about how they want routes to come in. So we should eventually see the metric as 20. Why is it not doing it? Oh, that's why, because I didn't put a no in front of it. Yeah, this will kill you on the lab. And the more and more you do this and mess it up, the more stressed you're going to be about completing the lab in time. So always check your work. Show run section router. All right, there we go. Now if I go to router 1, I should still be preferring the NSSA type 2, but the seed metric is the same. All right, so the forwarding metric for these external routes actually plays a more significant role than the seed metric. Not that the seed metric is not also considered, but the forwarding metric plays a very important role. So let's do one more experiment. Let's go ahead and, rather than have this be a 31, I want this to be a 33. So in this case, I'm going to go ahead and send, let's leave the loopback as 1. Let's leave the overall forwarding metric as 11. But I want to send in the route as a 21. That would make it a tie. So let's send the route in as a 22, which would make it 33. Clearly, I think in that particular case, you would understand that the E2 route would be selected over the N2 route because the overall path metric. Now, in that case, you might say, well, yeah, of course it's going to. The metric for the network is higher. 22 is higher than 20. But again, it's the forwarding metric that's critical as well. Okay, the forwarding metric is very critical. So you have to consider both. I don't know if that helps, Tim, kind of just, describe the path selection process. Only if there's a tie is the E2 route preferred over the N2 route. How could I make it a tie? Well, let's make it a tie by changing. Let's go ahead and leave this guy to the defaults, which it's already set to at this point. So we're sending it as an N route with a seed metric of 20. This is a 1. the forwarding address is going to add a 1, plus this is going to add a 10. So what we need to do is we need to make this an 11, okay? Which would make this path cost 31, and this path cost over here is going to be 31, okay? And in that case, because there's a tie, router 1 is going to choose the E2 route over the N2 route. So let's go to router 1. Interface Ethernet 1.0. Let me just do a show run. And let's go and say IP OSPF cost 11. Now if I do a show IP route 172.16.101.0, I can see that I am now still using the NSSA external. Show IP OSPF database. Pipe begin type 7. So I'm getting the 101. Show IP OSPF database external. And let's see, we're looking for the 172. .100 or 101, so right here. Metric is 20. Interesting. It is still preferring the NSSA type, the N2 over the E2. That is really interesting.
What's the forwarding metric for E2?
The forwarding metric is, well, let me interface Ethernet 1.2 shut. Do show IP route 172.16.101.0. So the forwarding metric is 11. Metric is 20, so it's 31. So that is interesting. It appears, although that really should not be the case.
Could it just be that you have to restart the process because it had that before, so it's going to maintain the route, and so you drop it?
Not typically with routing. I'm thinking, hold on. Not typically with routing. I mean, E1 should be preferred. And O route is always going to be preferred over OIA, and then E1 over N1, and then E2 over N2. That's pretty typical. That's what we usually see with regard to the preference. Let me turn the interface back on and see if it reinstates that N2 route. Show IP OSPF. Show IP route 172.16.101. So it is still using the E2 route. Nope, it switched over to the N route. So that's another interesting concept. Why would it be choosing an N2 over an E2 if there's a tie? Why would it be choosing an N2 over an E2 if there's a tie? Show IP OSPF database, NSSA external. Let's think about the recursion process. And I think it has to do with the SPT resolution, the recursion for the SPT, being that, let me see, let me find my 172.16.101. because I'm using a type 1 to recurse to this. I'm using a type 1 to get to the type 7.
Could it have something to do with the p-bit?
Well, the p-bit is enabled in this case. And the p-bit would only indicate whether or not the route could be converted or translated to a type 5. There is no p-bit in the case of the route coming from here because it's not coming into a special area type. The p-bit only comes into play if it's a special area type, right? Which that's the only reason you would ever convert a 7 to a 5 is if it's a special area type. So this goes against what I would have expected to happen in this case. But I'm sure we can figure this out. So R1 is recursing to using a type 1 LSA to get to the forwarding address here. And here we're using a type 5. We would have to use a type 5 to we would have to use a type 4 to recurse to the type 5 to then get to the external network. Because the router 5 is going to be generating a type 4 in the area as well because it's an ASBR. If I go to router 1, show IP OSPF database, I'm going to see a summary ASB for that router. So type 7, 101, type 5, 101, which we would expect to see. But, and unfortunately this is the way it is. Mike, I think you probably ran into this before when you were looking at documentation. I know you had a question about this at one point. So here's my type 4s. That's into area 1. So I'm originating the type 4s. I wouldn't be using the type 4. Do I have type 4? I should have type 4s into area 0 as well. Summary net. I'm trying to think of why it would be doing that. Why is it choosing? I'm going to have to table that probably and maybe play around with it and figure out why it's choosing the N2 route over the E2 route even though there's a tie. And when I was preparing this lesson, I referenced the RFC and also the Cisco documentation, and the selection process should be if there's a tie, we're going to choose an E2 route over an N2 route. But obviously there's some, I'm not going to say that this is not doing it correctly. There must be some other deciding factor in the event of a tie. Something that I'm not familiar with.
The only thing I'm seeing online is that if the p-bit is set, it could be the deciding factor that would force an N2 to be chosen over an
Well,
E2.
certainly I would agree with that, right? Because if the p-bit is set, or the p-bit is not set, or p-bit is set, that means the translation can't take place, which means it wouldn't show up in area 0 as an E2 anyway. It would only show up in the NSSA as a type 7. And I would have to use the type 7 to get to that external network because it's not being redistributed into area 0 as a type 5.
On the path, if you go back to the other router, if it's set there, could that be basically telling, like, over the whole route to use that, because why would you be translating anyway? So
well,
when
that's,
you set it to translate, you're basically saying, we want to go over this route.
That's the other thing that I'm thinking about, but we always would prefer an intra-area external route over an inter-area external route. And I think that's what's happening here is router 1 sees the external route coming from router 3 as an intra-area external route, as opposed to an inter-area external route. But that would really be what would apply. That has to do with the fact that I'm getting that route from router 5. Has to do with that. Let me think about that for a little bit. We know that there's multiple options. Okay. Let's take a look at the loopback on router 5. Hold on one second. So what we're trying to confirm now is we're resetting the external routes to get these updates to identify whether or not the p-bit is being set for those external routes. So let's do a filter, apply filter selected. And I'm not sure which one to look at here. Let's start with this one here. Type 7. There's your p-bit. Okay. Propagate. So it looks like in the case default behavior, the p-bit is set to indicate that we are allowing these routes to be translated to type 5s. Okay, so that answers that question, right? That's being done automatically in the redistribution process. So if I go to router 3 and I want to disable that feature, do show run section router, and I want to disable that feature, I go into router OSPF 1 and I say area to NSSA no redistribute. Okay, so that is indicating that the p-bit now should be disabled. I'm not sure if we're going to capture that in real time. Let's go ahead and trigger a change again. I mean, there should be a change. If I go to router 1, let's see if router 1 has already recognized that those routes cannot be translated. Show IP, OSPF, database, NSSA external. That's weird. I'm not getting my type 7s. How come I'm not getting my type 7s now? Show IP OSPF database. Begin type 7. Show IP interface brief. Maybe the interface is still off. No, it's up and running. Why am I not getting my external routes? Let's see. Let me clear the process. So I'm definitely getting DEX routes. I should be getting type 7s, but I'm not getting type 7s. All right, let's get the type 7s back in. It's a lot of S's. I need to get my type 7s back. Okay, so now I'm getting my type 7s back in area 2 from router 3. That's where the P bit is going to be set to obviously indicate that those routes can be converted. If I do a show IP OSPF database NSSA external, type 5 7 to 5 translation is allowed. Now, what I should be able to do is I should be able to change the behavior under router OSPF 1, area 2 NSSA. I wonder if I used the wrong argument. Should be no redistribution. Let me go back to look at our documentation here. Oh, it's only on the area border router. So in order for us to do the P bit, we would have to have this option, which limits the default advertisement to this NSSA by setting the P bit to 0. And unfortunately, we don't have that option in this code. Let me do one thing here. I'm not going to rebuild this, but I want to see if my IOSV router has that option. So Tim, in order for us to be able to suppress the P bit, we would have to do the NSSA only option, which is what I had talked about at the beginning of this lesson, which means that router 1 and router 5 would not be able to send those routes into area 0 as a type 5. But to answer your question that you had previously, the P bit is enabled by default, and by disabling the P bit, we're changing the behavior of how those type 7s can interact with the ABRs in the NSSA. That makes sense. I just want to see if this IOSV router supports that feature.
I'm wondering if it being set by default on router 1 is what's causing it, not on router 3.
Well, that's the thing. Router 1 is not originating the external routes. So the P bit is only set on the router that's originating the external routes. Router 1 is not originating the external routes. It's not originating the type 7s. See what I'm saying? So let me just check this real quick.
Yeah, but it's only transit between 5 and 7. Isn't it going in from router 1 into the NSSA?
Yeah, this doesn't have it either.
It's 5 and then it's translating it to 7?
You mean in the other direction?
Yeah. Yeah, doesn't it? I mean, and maybe I'm just, I'm not seeing this right, and that's why I'm glad we're in class, because
well, that's why we're here, yeah, to talk about it. So you're saying...
Router 1, router 3, doesn't it also go the other direction if you have the P-bit set? Like, because isn't it translating upwards or downwards? So, like, for instance,
no,
router 3,
no, and here's the reason why. Here's the reason why.
From 7 to 5.
No. I see what you're saying, yeah. 5s don't get translated to 7s because 5s are not allowed into a special area type regardless. Remember, stub areas, totally stubby, not so stubby, totally not so stubby, external routes are filtered, period. No external route would be able to come in. If that were the case, then this 198 route would be sent in to the NSSA as a type 7. That's not the way it works. External special area types do not allow external routes at all.
4? I mean, from area 0?
Yeah, router 3 does not have any external routes. If I go to router 3 and I do a show IP pipe include E1, E2, because that's how it would come in, or an N1, N2. All right, we don't see any external routes on this router because it's a special area type. Those routes are not allowed to come into the area, period. External, so the route is already being rejected before it's even sent in. See what I'm saying? Because it's an external route. Yeah, and NSSA and all the other special area types, a default route is automatically injected by the ABR to get to those external networks. But NSSA is the only one where that doesn't take place from the ABR, from the perspective of injecting a default route into the area. So that's the other part of our discussion, which was the next part of our lesson, is how do we get that? I mean, how do we control that default route that comes into the NSSA? But yes, there's no reverse translation. Yeah, go ahead.
Because when I'm looking at like on the Cisco Learning Network, people are putting in stuff. I'm trying to figure out, like they say, the only way that you can have N2 will be preferred over N1 if all things being equal, is if the P bit is set, and it looks like the P bit is always set. If you need to have that kind of a route.
You're talking about N2 over E2?
Yeah.
Well, we know that that's not true because we already seen that that's not true. This is one of
confused.
Yeah, this is one of the most misunderstood concepts in OSPF is the order of operations for route selection, and you can see why, right? Remember, we're trying to route to nodes, we're not trying to route to networks. So as long as the N2 path is better than the E2 path, then that path would be chosen, right? And we've already demonstrated that concept. The N2 path is definitely being preferred over the E2 path. The whole reason we got off on this tangent, though, is because if there's a tie and the overall metric for the N2 path is the same as the E2 path, then the E2 path should be chosen over the N2 path. But that's not the behavior that we're seeing in this particular case. We're seeing that the N2 path is still preferred over the E2 path when they're the same. And that's the part that's kind of throwing me off, because I've always expected, and again, I've never run into this situation in the real world because it's just not simply something that you would have configured in the real world. But the E2 path should be preferred over the N2 path if all other parts are equal, right? So the P bit, and I want to be very clear about this part because there's no confusion about this part. The P bit is only going to be set on an ASBR that's generating type 7 routes. And the only router that's doing that in this case is router 3. Router 1 and router 5 can't even disable the P bit because they're not the originators of the external routes. Router 5 is not generating a P bit. Actually, router 5 would be generating type 7s into area 2 for the same prefixes. And I'm wondering if that would be one of those options. I'm just trying to think about why. So router 1 is getting the 172.16.101 subnet from two different directions. It's getting the 172.16.101 from router 5, and it's getting it from router 3. From router 5.
Which one is preferred again, router 1 or going through router 3 or going through router 1?
What should be preferred is going through router 5.
Router 1. So that one's preferred, even that's the N2, correct? Or is that the E2? I'm getting confused.
All right, so if I do a show IP route, 172.16.101.0, right now we're preferring the N2 route. Okay.
And
The
back
seed
to
metric,
diagram and show me which one the N2 route is.
the N2 route's coming from router 3. It's coming from router 3.
So it's going from router 3 through to EIG. Oh, it's going that direction.
It's going this direction. Okay? But it also has a choice to go that direction. Now, if we've already determined that if the seed metric is the same, the seed metric being the metric that's being sent in the redistribution process, the seed metric is 20 on both sides. So we cannot differentiate between those external routes based on the seed metric.
Could it be that because on router 1 it's connected to the N2 routes, that it knows that that's where it's originating? It's always going to choose that if all things are being equal.
It doesn't make sense. It doesn't make sense because R1 is in area 0 and R1 is in area 2. So we can't really qualify this as an intra-area external versus an inter-area external, because when it's coming into here, it's intra-area, and when it's coming in from here, it's intra-area. You see what I'm saying? It's within the area.
Well, but what if we look at if we're on, say, R4, and we're trying to choose which one to go, will you even have the choice for N2 versus E2?
No, you wouldn't, because they're already E2 coming into area 0. The only decision R4 would have to make is recursing to the ABR, right? So right. It's whether or not I'm going to use a 1 to recurse to a 5, or if I'm going to use a 1 to recurse to a 4 to a 5, and so in this case, router 4 most likely would choose, based on this process, R4 should choose R5 to get to that external network because of the overall forwarding metric. Remember, the forwarding metric is included here because we're using see, if I go this direction, I'm using a 1 to recurse to a 3 to recurse to a 5, well, a 7 really, but it's basically a 5 because of this transit network here, right? I'm going to have to be able to use the 3 to get to the advertising loopback here. Let's go to R4 and take a look at that. So if I do a show IP route 172.16.101.0, I am going over to 14.3, which is router 5, which makes sense, right? I'm going to router 5 to get to that destination. If I do a show IP OSPF, show IP OSPF database external, what I should see is a quad 0 for the forwarding address for 172.16.101. So in this case, that means that I'm using a type 1 to recurse to the type 5 directly, because all I have to do now is recurse to 5.5.5.5, node 5.5.5.5. If I do a show IP OSPF database 5.5.5.5, we have a type 1 LSA to get to 5.5.5.5. So if I do a show IP route 172.16.101, the forwarding metric is 10 in this case. So I'm not even looking at, in this particular case, the cost outside of my area to reach that destination, because I don't even really know what that is, right? Because the ABR is advertising that transit link as a type 3 LSA, and again, I'm just going to use my forwarding metric to determine how do I get to the ABR, because I'm routing to nodes, not to networks. So if you look at, from router 4's perspective, the decision process here is a little bit different than from router 1. We're tabling router 1 for right now, but the decision process from router 4 is, you know, how am I recursing to the final destination? And in this case, I would have to recurse to a type 3 to be able to get to the type 5. Here I'm recursing using type 1 to get to the type 5. So I'm going to prefer that path because the forwarding metric, by the way, is the same. The forwarding metric to go to router 1 is the same as it is to go to router 5. Now, if I was to shut down the Ethernet 1.0 on router 5, and I go back to router 4, obviously in this case, router 4 is now going to recurse over to router 1 eventually. Come on. Did I shut down the right interface? Yep, I lost my neighbor on router. I lost router 4 and router 1, so router 5 doesn't exist at all. This is interesting. Now if I do a show IP OSPF database, oh, there we go. I got a switch in between, so I had to wait for the hold down timer to expire. That's where BFD comes in, very useful in that particular case, because the LAN connection on router 1 didn't go down, or router 4 didn't go down. We had to wait for the 40 seconds for our dead timer to expire. So now I'm recursing to router 1.
Hey, Scott, I'm going to jump in. I just read something that may make a difference on why N2 is preferred over E2.
Okay.
It says it's about the type of RFC that's used. Old versions of the iOS give the behavior that you were mentioning before, that type 5 is always chosen over. Hold on. Basically, the old way, it goes any type 5 LSA first, then it'll go to a type 7 LSA with E-bit forwarding, and then any other type 7. And that's with that's RFC 1587. The new RFC 3101 goes any type 7 LSA with the P-bit set, then a type 5 LSA, and then it goes to the LSA of the highest router ID.
Interesting.
I'll forward that over to you. I'm not sure again. I mean, this has been bothering the heck out of me.
Well, that would describe the behavior in the case of a tie. Absolutely. And that's what they're describing there. And that's what we have in our situation is we have a tie. But we know that the E2 route could be preferred over the N2 route regardless of the p-bit value, depending on the forwarding metric, right? Ultimately, that's what's going to change the decision. Now you can see here, I'm going to go back and describe what I mean by that in a second, but router 4 is clearly using router 1 now as the router of choice. And again, notice that the forwarding metric is a 21, which makes sense because if I do a show IP OSPF database external, we can see for the 172.16.101, the forwarding address is identified as 3.1, which is the loopback on router 3. But I also have to include the cost to get to router 3. So that is 10 here, plus 10 here, plus the 1 here, plus the seed metric, which is why we're now using that path. So the decision from router 4's perspective is pretty simple. Am I going to choose the path through R5 or am I going to choose the path through R1? And it has to do with how we just recurse the routes because they're both coming in as E2. the forwarding metric is the The forwarding metric is what's forcing us to make that decision. It has nothing to do with the actual seed metric, because the seed metric is the same. That's kind of my point. The seed metric from R5 is 20. The seed metric from R3 is 20. And then you might think, well, I might load balance to get to those external networks through R1 and R5, but the forwarding metric is always going to be considered in the decision as to which node we're going to route to. Okay? So let's go ahead and turn on Ethernet 1.0 back on router number 5. And let's go ahead and test that other theory, Tim, because based on what you described, they're stating that an N2 route with a P-bit set would always be preferred over an E2. And that's absolutely not the case. So it is apparently the case in the event of a tie if the P-bit is set. So we can't turn off the P-bit in this code, and I'm not sure what the if that's been a deprecated command, or if that's because this is fairly new code. I'm talking about the option to do the NSSA only when we're setting up our NSSA. But let's go into router 3. We already know that the P-bit is being set in the type 7 LSAs. Let's see what router 1 is choosing as of right now. Show IP route 172.16.101.0. So we're using the NSSA type 2. The forwarding metric is 11. The seed metric is 20. Now, based on that, if I come into my topology and I shut down Ethernet 1.2 on router 1, clearly it's going to go over to router 5 using the E2 route, but I want to see if the values are the same. So interface Ethernet 1.0, we'll shut that down. Do show IP route 172.16.101.0. So now we're using, once we converge here, did I shut down the right interface? I did not. No shut. Let me go into Ethernet 1.2. So now we should be using the external route as soon as I convert. There we go. So the external type 2, seed metric is 20, forwarding metric is 11. If I go all the way back up to when we had this as an NSSA, same variables. Seed metric is 20, forwarding metric is 11. So that being said, it appears, and this is maybe based on that documentation that you have there, Tim, is that as long as the P-bit is set and there's a tie, we're going to choose the N2 route over the E2 route. However, if I go into do show run interface Ethernet 1.0 and I remove this cost, now if I do a show IP route, I should see in this case that the forwarding metric should be 10 for that path. The seed metric is still 20. And if I go into interface Ethernet 1.2 and do a no shut, the N2 route is not going to be preferred over the E2 route because there's not a tie. The forwarding metric is less using the E2 path than it is using the N2 path. All right, so let's see if that's the case. Yep, and we're still using the external type 2 path. So we're using E2 to get to that destination because the forwarding metric is less than the forwarding metric of the other path. Does that make sense?
Absolutely, and even the RFC states it. That's just a tiebreaker that it's doing.
Okay.
At least, so it looks like this might actually be solved.
Yeah, it looks that way. I wish we could turn the P-bit off to see the behavior otherwise, but yeah, it looks like, and again, it's kind of one of those things that you kick yourself about because, thank you for looking it up, Tim, but it appears to be a case-by-case basis, right? Depends on what version of code you're running as to the behavior. So we're running 15.2.4. We're not running IOSV in this case. We're running actual code 15.2.4. So it looks like, did it indicate what iOS version that would have been affected in?
Yeah, hold on a minute. Let me go pull it back up.
All right.
Yeah, if you're doing anything under 15.1.2, it would show the other behavior that we originally thought. Anything 15.1.2 or over, it has new behavior where it will do a tiebreaker for people.
Okay. All right. Well, you're going to be running 15.2 or above on the lab anyway, so now you know what to look for from that behavioral standpoint. All right. So if I did we should see the same thing if I do a show IP route for 55, 55, 55, 55 as well. Yeah. So because that's coming in, but I mean, that's being originated by router 5 anyway, but it's still coming in with a forwarding metric of 10 and it's coming in as an E2 metric 20. Okay. Trying to think what else I wanted to show you guys in this lesson here. There were several other things that I wanted. As you can see, the overall path selection rule process is extremely complicated, very complicated. Okay. If the p-bit was not set, there may be another way that I can change the p-bit value. Let me try this. I didn't think to do this, but I'll bet you I could do it on the I could probably trick the router. Let's go to router 3. I just thought of this. Let me try this because I bet you this will work. Router OSPF 1. Summary address 172.16.101.0, but we're not going to use this to do an aggregate. We're just going to use this to turn the p-bit off. Now that should disable the p-bit on for that network. There was two ways you could do it. You could do it under the routing process, or you could do it using a summary address command. So you could do it. It's interesting. It allows us to do it there. You could do it when you're defining the area NSSA, where you do NSSA only. We don't have that option, so I'm doing it with the summary. Let's see if that worked. Now, that being said, let's go back to router 1. And we're going to change the match. We're going to make it a tie again. I'm going to change Ethernet 1.0 to 11. IP OSPF cost 11. Show IP route 172.16.101. There you go. The p-bit is now not set, so it's preferring the external type 2 over the N2 route. I'm very proud of myself for figuring that out. Let's do interface Ethernet 1.0, and let's shut that interface down. Okay. Now let's do a show IP route. We should be using the N route now. Do show IP route 172.16. Yep. Now we're using the NSSA route. Now let's see if the p-bit is set on that. Do show IP OSPF database NSSA external 172.16.101.0. p-bit is turned off. So we finally made it to the finish line. I knew we would get there eventually. So what I did is I tricked the router by creating an aggregate, a summary address. You can summarize on an ABR and you can summarize on an ASBR, but I didn't actually create an aggregate route. I just summarized the route that already existed, which was the /24 route on router 3. But I added the NSSA, do show run section router. I added the NSSA only option, meaning that we were going to generate this aggregate route as a type 7, but it was not going to be translatable to a type 5. In other words, we were able to set the p-bit off by using an aggregate address. Does that make sense? So even though the NSSA only option didn't exist in the version of code that we have, we could apply the NSSA only option to our aggregate summary, which is not technically an aggregate summary. It's just, we're summarizing what we already have, which is a /24. So now there's a tie between the E2 route and the N2 route. There's a tie, but the E2 route is preferred over the N2 route because the p-bit is off. But if the p-bit was on, the N2 route would be preferred over the E2 route in the event of a tie. You guys follow? Do you guys understand what I did there?
Yep, makes sense.
Okay. Let me see here. Yeah, Tim put that in the chat window there. How many people have we lost? Let's see. Kamal's still here. Hey, Kamal, how you doing? Mike is still here. It looks like we only lost. Who did we lose? Ken. We lost Ken. Ken disappeared. All right. Wow. So, I mean, this is good. This is why we're doing these discussions, right? Why we're having these discussions, because this is the kind of stuff you're going to run into that's going to drive you crazy. Whether or not you decide to remember this later on or not, that's a completely different story, right? Even me, I'm not as well versed in these quirks as well. I mean, when I did my CCIE, it was very simple because we were using a different version of code. We were using 12x code. We didn't have to worry about it because the selection process was pretty static. All right. So all we were doing in this case is we're not really trying to summarize or create an aggregate route. All we're trying to do in this case is alter the p-bit of the LSA so devices outside the NSSA are no longer going to have a route to that particular prefix. All right. This is what we define as a type 7 that has an area local scope, meaning that the type 7 is being sent in, but it only has an area local scope. All right. What is the point of being able to do any of this stuff, by the way? Any thoughts?
Don't get all existential, Scott. We're trying to get our CCIE.
Traffic engineering, right? I mean, think about it for a second. Router 4 is going to be able to reach 55, 55, 55, 55, which is, by the way, a type 7 LSA that's being generated well, it's actually being, yeah, it's being generated by, well, let me actually demonstrate that concept. So it's actually not being generated as a type 7 because it's coming directly off of router 5, right? So if I shut this interface down, router 4 should not have any reachability to this LAN, but it still should be able to reach the loopback on router 5 because we're not altering the P bit on the loopback. That's coming in as a type 7 from here. You see what I'm saying? So let me shut down on router 5. Let me actually make sure that my interfaces on router 1 are up. I think it's this one. Show IP interface brief. Up, 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 up. Okay. So we should get our adjacencies back. So if I go into router 5 and shut down Ethernet 1.0, and I'm going to have to wait. Let's just do a clear IP OSPF process so I don't have to wait the time to. Okay. I should still be able to ping. Let's do a trace route. I still should be able to reach 55, 55, 55, 55. Yep. Oh, it's sending it out to the internet. Hold on. Show IP route. Network not in the table. R5 should still be originating that route. Oh, you know what? It's not going to work. Well, actually it should. Do show IP route. 55, 55, 55, 55 is connected. And R3 should be sending that route. Show IP route. Show IP OSPF database. Self-originate. I should be generating that. Yep. 55, 55, 55, 55 is coming in as a type 7. Do show IP OSPF database NSSA. It could be a convergence thing, or I forgot to turn on an interface do IP show IP OSPF database NSSA 55, 55, 55, 55. So the P bit is definitely set there, but if I look at 172.16.101, the P bit is not set. Okay, which means that router 3 in this topology, excuse me, router 1 in this topology should be able to translate 55, 55, 55, 55 to a type 5, but not this network here. Let me make sure I've got all my interfaces turned on.
What's the address you're trying to get to again, and which router is it on?
55, 55, 55. Okay, which is on router 5. It's a loopback on router 5 in EIGRP.
So you have Ethernet 1.0 turned off?
On router 5, yes.
Well, then, so and if it's going through an NSSA, it's the only route you're going to be able to get to it. No, it can't. Well, unless you can, if it goes.
Well, I mean, the loopback is going into EIGRP, and router 3 is redistributing EIGRP. Okay. And so router 1 should just be sending that over to router 4. It could just be a convergence thing. Let me show IP Ceph 55, 55, 55, 55. Yeah, it's in there now. Yeah, it was just a convergence thing. You understand how that's getting in there, right, Tim? Because the p-bit is set. Chocolate pretzels. Okay. Right. Exactly. So 55, 55, 55, 55 is coming in as a type 7, but because the p-bit is set, it's allowed to be converted to a type 5 on router 1 and sent in, but because we did a fake aggregate, summary aggregate on ASBR router 3 and did NSSA only, disabling the p-bit, the LAN segment's not allowed to traverse router 1 and get converted to a type 5. That makes sense?
Yep.
And the problem is, and this is the issue you run in with OSPF, is that you can't just say I'm going to change the cost of a link to influence path selection. Certainly you may be able to influence metrics to decide whether or not you're going to use a E1 or an E2 or an N1 or an N2, but as you can see, it's not always hard set, right? We may be deciding on choosing a path based on other values, like a p-bit value or a or some sort of obscure decision process that we had to discover today about whether or not the p-bit is set and it's an N1 or an N2 or an E1 or an E2. All right. I mean, honestly, if you're because we're not routing essentially based on the route, we're routing based on the shortest path to the different nodes in the network. If you really need this much granularity, where you're doing this kind of traffic engineering, you're better off utilizing BGP, right? The BGP topology is or hierarchy is arbitrary. You're just using path attributes to make decisions. The reason why I wanted to do this lesson and I wanted to get into this much detail, which I knew it was going to be complicated because it's a very complicated topic, is they could ask you specific questions. So it's important to understand the arguments that exist with these particular networks. All right. You might decide to do something like this to avoid loops. And OSPF, in any event, is always going to use the exact state machine for path selection anyway, right? Because that's the whole loop avoidance mechanism in OSPF. You might have a shorter path in a different direction, but because we don't necessarily have visibility end to end, I would choose, say, for example, an intra-area route versus an inter-area route. Okay. There are other options. No redistribution. We already talked about that one. That means that we're not going to allow, if I've got an ABR that's also acting as an ASBR, I'm not going to allow the type 7s in the NSSA, but I'm going to allow the type 5s, right? So we'll allow routes to go in as a type 5, but not in as a type 7. Also, we may want to try and provide some sort of control as to what direction we might decide to do our default route. That's why in this particular case, in the NSSA case, and it's the only special area type that does this, a default route is not automatically injected into the area, because it gives us the ability to do this traffic engineering to identify what the best path is going to be. We're going to choose a 3 over a 5 over a 7 in certain cases, as we've already seen. The p-bit, in the case of no redistribution, is not set. I'm already sending the route in as type 5. I don't want anybody in the area in that NSSA to translate those type those type 7s back to type 5s, creating a loop. Basically, no redistribution, and I demonstrated this earlier in the lesson. No redistribution means I'm not allowing that ABR that's also acting as an ASBR to generate a type 7 into the NSSA. All right. Now, what if I did want to generate a default route into the NSSA, right? We can do that. Let me fix my routing here by doing a no shut. And we should see that we're now going back to router 5 for this. Once we get our convergence, we should be going back to router 5. There we go. For the 55, 55, 55, 55 loopback. Okay? But what about reachability in the other direction? Right? For example, we've got in our topology, we've got this external network, 198.51.100.1. Well, router 3 doesn't have any visibility to that network because that's a type 5 LSA. It's being redistributed by router 4, and it's coming into router 1 and router 5 as a type 5. Because this is an NSSA, that type 5 is being blocked. But I don't have a default route. I could certainly do a static default route, but they might tell you on the lab, you're not allowed to use a static default route on router 3. And by the way, you may not want to do that, right? You may want to, if you use a static default route, you don't have any redundancy or failover, so you may want to somehow inject a default route into this NSSA. It's actually a pretty simple concept. If we go to router 1, router OSPF 1, area 2, NSSA, default information originate, and router 5, router OSPF 1, area 2, NSSA, default information originate. I can also specify the metric type. Is it going to come in as a type 2 or a type 1? And what the seed metric is. Now if I go to router 3, do show IP Ceph 198.51.100.1, we can see that we actually have reachability to that destination. If I do a show IP OSPF database, we can see that we're actually getting a type 7 in now. That's a default route. So we're breaking the rules, if you will, a little bit of type 5. Well, external routes are not allowed, but what's happening now is that both of the ABRs are generating a type 7. How I decide which way to go is going to be dependent on how I recurse to those particular destinations. So if I do a show IP OSPF database and NSSA external, and I look for the quad 0 routes, which are right here. So I've got router 1 that's generating this quad 0 route, and I've got router 5 generating the quad 0 route. But if you look at the metric, the seed metric is a 1. Okay? But because the forwarding address is quad 0, I'm going to recurse to this default route using a type 1 LSA. So if I do a show IP OSPF database router 5.5.5.5, we can see that the metric is 64, and if I do 1.1.1.1, the metric is 10. So I'm going to use the SPT to calculate the best way to reach the originating router, if you will. And a quad 0 originating address means that that's the router that's actually originating that external network. All right. So we sent in a default route. Now, if I had done that, obviously to one router versus the other, then I would only be able to reach that external network from one of those ABRs and not the other ABR. All right. The NSSA is the only special area type that doesn't automatically send in a default route. So they may actually have you do that as well. they may manipulate, they may say, let's go ahead and manipulate how the path selection takes place by, let's prefer router 1 for my default traffic over router 5. All right. Now, in that particular case, I could set a different seed metric, and by setting a different seed metric, it's going to increase the overall path cost. So let's say let's make router 5 more preferred. So I would have to somehow set the seed metric on router 1 to be more than router 5. That would mean that the cost of that serial link is 64. So if I set the seed metric to 70, router 5 should be preferred. Let's do that on router 1. It doesn't have to be 70. I'm just picking a number that's higher than 64. So do show run section router. The other option would be, is E2 going to be preferred? Is N2 going to be preferred over N1? Let's do that first. The argument should be that an N2 route should be preferred, an N1 route should be preferred over an N2 route regardless. So let's make, I'm not saying that that's actually the case though, because we've already seen that our assumptions aren't always accurate. Let's make this one an N1. Let's leave this default information originate an N2. So if I go to, yeah, go ahead.
Can we go over why you would always pick, well, normally you would pick an N1 over an N2? Is it the routes? It's basically you're just taking the first metric? Or what's the criteria that you typically usually always pick an N1 over an N2?
The criteria, because I'm trying to think. It probably, I don't know the exact answer to that, Tim, but I'm thinking it probably has to do with the visibility of the overall metric, because an N1 route will the metric, the seed metric, will be accumulated as you move through the topology, so that when you do see the metric of the route, it's going to be representative of the overall path metric as opposed to the N2. But in considering the recursion process and how a router decides how to reach a node, it doesn't really make a whole lot of sense, because in either case, we still would be looking at what is the cost for me to reach the node that's originating the route. The cost for me to reach the node should take precedence over the type of route. Let's test that theory, right? Because I may be completely wrong. Maybe that in the modern sense, iOS sense, the N1 route is not going to be preferred over an N2 route. So let's go into router 5 and send this in as a metric type of N1. All right, and go to router 3 and see how it's deciding. Do show IP 198. 51.100.1. Okay, so it looks like in this case, well, that's interesting. Oh, the link is still shut off. Like, why is it using EIGRP to get there? That doesn't make any sense.
So here's the definition, and this is making it more confusing for me. But so E1 or E2 or N1 or N2 type routes are based upon costs of the route, whereas E2 or N2 routes tell OSPF routers to set the metric as a metric at the point of redistribution at the ASPR.
That's true. I agree with that statement, because what they're saying is
it adds internal costs to the ASPR to reach
yes
redistribution. So shouldn't E2 be always preferred?
Well, no. What they're saying is they're basically just describing the difference, right? They're saying an N1 route or an E1 route is going to add the cost of the links along the path to whatever the seed metric is to determine the overall path metric of that particular route. And the opposite is said for E2 or N2, where the cost of the route is just the seed metric, and then we have to determine the internal path cost, how we resolve the tree to get to the originator of the route. What I'm trying to figure out, though, is what would happen if there was a tie, right? Let me do a show IP OSPF database NSSA. So in this case now, this route from router 1 is coming in as a type 2. This route is coming in as a type 1. So if I do a trace route to 198, I mean, it doesn't really matter where I go. Well, that doesn't look good. That looks like a loop. It's going to 3 to 1 to 3 to 1 to 3 to 1. Let me do a trace route to a real network. Yeah, we've obviously been kind of piecemealing this config together, so there's a lot of stuff. We've got a loop somewhere, default routing loop, which doesn't surprise me actually, because we've got a bunch of people generating default routes, and we've got mutual two-way redistribution here. There's all kinds of weird things going on. 198.51.100.1. So router 5 is going to router 2. I mean router 4, that makes sense. Let's check router 3. So it's going to 100.10. It's using the EIGRP route. Why is it using the EIGRP route? DEX has a lower administrative distance than a higher administrative distance than to show. So we're getting a default route. Am I misreading this then? Because it looks like it's going to 130.1, 131.1, which is exactly what we would expect. The N1 route is preferred over the N2 route, even though it's a worse path. The serial link is going to have a higher path cost. It has a cost of 65, whereas the N2 route would have a cost of 10. But why is it? Maybe I'm just misinterpreting the trace route here. No, it says 100.10, 101.5, 14.2. That is really strange. So it's taking this path, but the default route in the routing table is this path. Oh, longest match. Because we're redistributing that route. It's coming in as an OSPF route, and then it's getting redistributed into EIGRP as a prefix, right? So if I do a show IP route, pipe include 198, yeah. So it's coming in as a /24. That makes sense. Let's stop redistributing that on router 4. Just to confirm our suspicions, which we can already see from the routing table. Show run pipe section router. And I'm just going to take off redistribution. And I'm just going to do a default information originate. Router OSPF 1, no redistribution connected. Default dash information originate always. So router 4 is going to send in a default route. Now if I do my trace route, I should see, nope, I got a loop now. Do show IP route. Yeah, we got some weird stuff going on with our default routes, but in any event, we know from this, and I think my computer's going to reboot in about 10 minutes, so we're going to have to wrap this up, that the default route, the N1 default route, is being preferred over the N2 default route. To prove this, I just simply want to go in here and I'll shut down this serial interface, and then the N2 default route should show up on router 3. So if I go into router number 5, and interface serial 20, shut that down. Now if I go to router 3, now I'm getting the, I should get the N2 route as soon as we'll have I don't have an interface in between there. Why is it not? Let me clear the process. Well, that's good. We got rid of our loop. So now we've got our ON2 with a cost of 1 coming from 13.1. So the reason I did that is I wanted to prove that the cost was less, right? This N2 default route that's being sent in has a cost of 1. I'm not sure why it has a cost of 1. I think with the default information originate, the default seed metric is 1. Yeah, that makes sense because the other one had a cost of 65 and the serial link is a 64. So unlike like a redistribute, the initial seed metric is 1 coming in. The seed metric here is 1, but because this is coming in as an N1 and this is coming in as an N2, we're adding the cost there. Actually, we're not adding the cost at all there. So that's coming in as a 1. We're adding the cost there, so that's coming in as a 65. But the N1 route in this case is preferred over the N2 route.
But wouldn't you also, anything that's a default route would never take precedence over another defined route?
No, yeah. I mean, you're always going to do longest match routing, right? That's always going to be the case. And that's why I was using the EIGRP path to get to the 198.51 network, because 198.51 was being redistributed into OSPF and then being redistributed into EIGRP. So the EIGRP path was being preferred because it had a 24-bit prefix as opposed to a /0 on the default route. But we've eliminated that by not redistributing 198.51 into the network and relying solely on the default route. But we had, because we're doing mutual redistribution here, and we're injecting a default route here, and we're injecting a default route here, and we're injecting a default route here. We got a loop here. We got all these crazy things going on. Obviously, from a default routing perspective, we need to kind of consider how those default routes are being sent in. We would not want to redistribute the default routes into EIGRP. Well, we would probably redistribute them and tag them so they wouldn't be redistributed back out into OSPF. And that's where the loops are coming in. But we don't have time to kind of go into all of those details in this case. But all right. So does that make sense? In this case, it appears that the documentation is completely accurate. An N1 route is going to be preferred over an N2 route regardless of the metric. Okay?
Is way of forcing an as an N2 route over an N1 route?
I don't think so.
I'm not.
I don't
So
think
I guess
so.
the only way to get to it is if you wanted to go is to change the route type.
Change the route type, yeah, because changing the metric would make no difference. Because the bottom path, which was N1 anyway, the metric for that path was much worse anyway. But it still preferred that path. Does that make sense?
So if we want to force something to go out the same route as the default route, can we change that to, and then, basically change the GRP path to an N2, and then change the default route the one that's going to WAN 1, change that to and then N1.
I don't think I can do that. I don't think it's going to make a difference because longest match routing is always going to take precedence over the deciding factor within the protocol. But let me go ahead and do that. So that's going to come in as a type 2. Well, actually, you know what? I can't do it, Tim, in this case. There's no way to change that route to an N1 or N2 because it's not allowed in the NSSA anyway. The 198 route is never going to make it into Area 2 because it's a type 5. See what I'm saying?
Yep.
I wonder if I could. Let me check something on router 3. Now
So
we're really.
You can't by a default route, and then when you put that default route in, change the type, the link type, not the link type, the router type. Or LSA.
Say that one more time, Tim.
So when you're going from router 3 to router 1, you can't change the type, the route type.
Yeah, when you're sending routes from EIGRP into the area, you can change the type. So you can make it N1 or N2 there. But remember, this route here is coming in here as an E2. You're not going to be able to send that E2 into here because this is a special area type. What I was thinking, though, I understand where you're going with the logic. Is there a way that we could... so it's already being redistributed into here. I checked router 3 and it shows up as a DEX route in router 3. So could I send that route in there as an N1, as an N2, which would have a longer prefix match, and then have my default route come in as an N1, which is a /0, and see if that N1 route is going to be preferred over the N2 route, even though it's a shorter mask, right?
Right.
So what I will do is let me shut off router 5's serial interface. Okay, to make this simpler. I'm going to go into router 1 and I'm going to do a default NSSA default information originate. Okay. And N1 should be preferred over N2. But I'm going to send this in. Oh, good. It gave me an option now. 4 hours later. I'm going to send in the default route, do show IP, OSPF, database, NSSA. So now it's coming in as a one. It's coming in as a type 2. All right. Did we say that type 1 would be preferred over type 2? Yes, right?
Yes.
So I want to send this default route in as a type 1. Show IP route, show IP OSPF database, NSSA external. So now it's coming in as a type 1. Now the question is, see, this is going to be a challenge. I've got to, well, from router 3's perspective, I've got to figure out how router 3 is going to choose to route to the 198 network. So let's go to router 3. It's using the DEX route right now.
So, and I'm probably using the wrong term, but so if we want to, if you're going from router 3, going to router 4, for instance, are we, what is the type going that direction if you're going through DEX?
Well, there is no type. It's just EIGRP.
All right.
And that makes sense. So what we have to do.
So now, does it automatically choose? Would it choose EIGRP in order to, because it's got a?
Well, it's gonna choose EIGRP because it's not learning about the 198 network from router 1. It's only getting a default route from router 1, and there's no comparison of N1 versus N2. What I would have to do is add another router. I mean, we're already going down this path. We might as well continue. I would have to add another router to the area. And connect this router to router 1 and router 3. So that it can learn this information from so let's make this network 172.16.16.0/30. And let's make this network 172.16.36.0/30. One 0 to 1 3. Bear with me a second here.
So you're going to make them N2, right?
Well, I'm going to give router 6 a couple of ways to learn how to get to the 198 network. You see what I'm saying? And this link here is Ethernet 1.1 to 1.3. You follow what I'm saying?
are. And so if you're going to give out different ways, but the default route is still going to go
Well, that's what we're going to decide, right? So
down, and then
interface.
it's going to take that, even though it's the
Interface
default route.
Ethernet 1.3.
So do we have to give, since they're all /30s, do we have to give the what's going for router 6? Do we have to give that like a higher cost, a higher number?
What do you mean?
Oh, I'm sorry, like make it like a slash.
No, I'm just going to make it 16.2.
Yeah, I guess it really doesn't matter as long as we have one as the default route. If we have R3 to R1 directly as default, and then
Right. Router 1, Ethernet 1.0. Oh, dang it. I can't do that. How can that be Ethernet 1.0? 1.3. Shoot. Change the wrong interface. 16.14. I don't know if that was the right address before or not. Ethernet 1.0 on router 1 was... this doesn't match. Oh, it was .2. That doesn't match at all. It's 14.2. Yeah, these numbers aren't right, but let me change this. Interface Ethernet 1.3. Ah, jeez. (14.2) on router 4. (14.3) on router 5, so it must have been 14.1. All right. I should get adjacencies now. To 4 and 5. Oh. Okay, I should get my adjacencies back. Now let's go into interface Ethernet 1.3. 172.16.16.1. IP OSPF 1 area 2. I'm not getting adjacencies. Why am I not getting adjacencies?
Hey, Scott, there's nothing to do with it being area 0, is there?
Well, that interface should be in area 0.
Wait a minute.
This interface should be in area 0. I screwed it up because I screwed up the IP address. I configured the wrong interface. But now I'm not getting adjacencies on my Ethernet 1.0 link. And I'm trying to figure out why. Let's cheat a little bit. Router OSPF 1.
Is that 1 or 1.0 that we're working on now?
I'm on router 1, Ethernet 1.0.
Wait a minute. Well, that should be area 0 then.
Ethernet 1.0 and router 1 is in area 0. This is documented incorrectly. This is Ethernet 1.3. See? That's what screwed me up from the beginning.
Yeah, that screwed me up. I was looking at it and I looked over.
But now I'm trying to figure out why I'm not getting adjacencies with router 4 and router 5. Oh, it's a 128. That's why. All right. Wonder if I changed that. I must have changed that interface. So I was trying to figure out why I wasn't getting a stupid adjacency. I should now. There we go. All right. Now let me go to router 6. Because I should already have an adjacency to router area 2 NSSA. So it's got to be on router 1. And the interface is shut down. Interface Ethernet 1.3, no shut. All right, now I just need to configure the link between router 3 and router 6. Config T interface. Let me make sure I get the right interface this time. Ethernet 1.1 goes to Ethernet 1.3. IP address 172.16.36.1. No shut. IP OSPF 1 area 2. And let's go to router 6. One 172.16.36.2. No shut IP OSPF 1 area 2. Sorry guys, my batteries died. All right, so now that we've got all of our convergence done, let's go to what we actually wanted to test in the first place. Let me grab another snippet of this topology here, and this will be the last thing we do. We'll wrap it up. Obviously, we're not going to get into lesson number 2 today, but that's okay. We can do that on Monday. All right. No lessons on Mother's Day. Sorry, guys. I know you want to get out of doing Mother's Day stuff, but all right. So we've got this route here being sent in. Because this is an NSSA, it's not going to come into that area as a type 5. So we're sending in a default route here as an N1, but that's a /0. R6 should have a type 7 from R3 because that route's being sent into EIGRP and it's being redistributed back into OSPF from R3. So R6 should have a prefix of 198 in its routing table. Show IP route pipe include 198. And sure enough, it does. Now the question was, is that route going to be preferred over an N1 route? And the answer is obviously, it's not obvious or else we wouldn't be doing this. Even though it's an N2 route, the N1 route is not going to be preferred because we're doing longest match routing first. So if I do a trace route to 198.51.100.1, you can see that I'm going 236.1, then over the EIGRP network, and then to the router. So in the case of the routing, if you will, the decision tree, longest match routing is always considered over anything that would be decided within the protocol itself. Does that make sense?
Yes, so if we did this from R3, we would get the same result, I'm assuming?
Correct. Now, let's do something on R3. I promise this is the last thing we're going to do. Summary. Well, I don't know. I can't do it as a 0. I was going to say I was going to do an aggregate to make the prefix longer, but I can't do an aggregate to 0, right? If I do an aggregate to 0, that's a default route, and then I'm just sending in a default route from the ASBR. So yeah, so to answer your question, Tim, router 3 is going to choose this path because of longest match routing as well. The 198, even though it's an EIGRP route and it has an administrative distance of 170, longest match routing takes precedence over everything, even administrative distance.
That's very good to know or to be able to see through them. So if we see this, we're not going to be wasting our time trying to go through and just analyze where the path is.
Right. So see, the DEX route is the DEX route is, but if I do a show IP route, we can see that we're getting a default route with a lower administrative distance, but longest match routing is going to take precedence over everything else. All right, guys. Well, that was a long one, but longest one so far. But it was also one of the more complicated discussions that we typically have. So I appreciate you guys spending the 3 hours with me, actually longer than 3 hours with the breaks that we took. But we're going to wrap up this lesson. And let's talk a little bit about what we're going to do the